think you'll find this to be pretty straightforward in terms of the subject matter. We're all familiar with what we call states of matter. In that it's simply the solids, liquids, and gases. So in the concept that we're about to talk about, we need to understand and compare what differences in solids, liquids, gas in terms of the kinetic molecular theory. Now, as we start our study of states of matter, we need to have some scientific method by which we can describe the solids, the liquids, and the gases. Well, we know from the kinetic molecular theory all matter is made up of particles. Molecules, elements, and so forth, like that. And these particles interact by attraction. Put interact. Interact by attraction or repulsion forces. So it is these attractive and repulsion forces that we want to look at in terms of forming solids, liquids, and gases. Solids, of course, have a particle-particle interaction, and so they live close together. And then liquids are a little further apart, a little more fluid, and gases do not have a high inter-particle attraction from one another and certainly live far apart from one another. All particles of solids, liquids, and gases at nominal temperatures are in motion. And these are divided into three modes of motion. Translation, rotation, and vibration. Translation is, of course, point to point, where it moves straight line to maybe collide with another particle and then off another straight line. Rotation is self-explanatory and rolling motion. Vibration, oscillating particles. Now, when we talk about solids, liquids, and gases, we talk about them in terms of how much motion do the particles have relative to a solid, or relative to a liquid, or relative to a gas. Well, obviously, if we're talking about gases, we have a high degree of motion in all three modes of motion. If we're talking about liquids, we have a reasonable degree of motion, if I could specify it that way, in the three modes of motion. And then solids are very restricted. Now, you do have translation, migration of particles in a solid, and rotation to a certain degree, but they are very, very limited. Now, vibration depends on the amount of energy contained in the substance. It's kind of a thermodynamic issue, but you have a high degree of vibration, but you do not have a high degree of rotation translation for solids. So you describe them kind of intuitively this way. I think anybody that would know these three, and I said, well, how can you relate solids to these three? Well, it'd be pretty easy to describe. Limited translation, rotation, and a high degree of vibration. But liquids, you start moving particles further apart. Particles have more energy and are less interaction, and then you get to gases. We'll talk about the different interactions in a little bit. Okay. And we talk about collisions between particles, or, as you recall from gas walls, we talked about kinetics a little bit. They are elastic, perfectly elastic. So collisions between particles are perfectly elastic. If I can get all this on one page, or and if you recall, what that means is that no energy change is taken into account. That is, the sum of all the changing energy is equal to 0. So in reality, particles collide, they lose a certain amount of energy in heat of collision, and they absorb light energy, which promotes them to a higher energy level. Well, all that's going on, but in the kinetic theory, we just say, okay, they're colliding, but they are not losing energy. Okay. In this topic, is very familiar to all of you, changes of state is melting, freezing, boiling, evaporation, condensation. Maybe some of you know about sublimation and deposition and so forth. Now, the way I present this is what we call a phase change triangle, or phase triangle. Here I put gases as around a cloud up here, and then I have a solid over here like this, and then I'll have a little puddle over here of a liquid. So we have solid, a liquid, and of course the gas. And so the terminology of this is probably going to be very familiar to you. Okay, simply put, if we go from a solid to a liquid, it's melting. Okay, so like that, and vice versa. If we come from liquid to a solid, it's freezing. Okay, now if we go from a liquid to a gas, boiling or evaporation. And of course, going from a gas to a liquid is condensation. And then a little less familiar to many, when we go from a solid to a gas phase without going through the liquid phase, the pathway is sublimation. Now, many textbooks, can you read that? Wow. I'm trying to, oh well, okay. I can get it all in here. Sublimation, going from solid to the gas phase. Many textbooks will use the same word, going from gas to a solid phase, and some texts will use deposition. This is DEP, deposition, right there. It's like making a deposit. Frost is a good example for this, in terms of going from vapor, water vapor, into ice. Frost is a good, R-O-S-T, is a good example for deposition. And a lot of times substances are purified by evaporating solids. Mothballs, paradichlorobenzene is used, and the smell from it. And mothballs don't go through they don't melt, they just sublime. They just go into the vapor phase. Dry ice, if you've ever seen it melt or go away, it undergoes rapid sublimation into the gas phase without going through the liquid phase. So terminology is very familiar to most of you, and I don't see any serious problem in beating that to death. Okay. Okay. Now, okay. What's vapor pressure? Vapor pressure is the pressure exerted by a pure gas in contact with its pure condensed phase. We're going to use the symbology VP like that. So, vapor pressure Okay. Vapor pressure in contact with this pure condensed phase. Water, for example, is a good familiar item. If we have a container of water, we will find that water molecules will escape from the surface. Evaporation, and if you want to make a note here, is referred to as a surface phenomenon. I guess a surface phenomenon, meaning that only particles that are next to the surface of the gas phase, will evaporate. The internals of molecules are all held in place by attractive forces. So we get a few particles that will evaporate and they will be moving around. Now, if we cover the container, eventually in time, as a function of time, the concentration of vapor up here will become saturated. Of course, they are in constant motion, and if you measure the pressure exerted by the particles bouncing around, if you had a gauge on the side here, some sort of pressure gauge, then it would be the vapor pressure of that liquid here. If you're talking about water, and this would be water vapor. Okay, so in essence, at specified temperature, the liquid would have a specific vapor pressure, like that. Now, what happens as the temperature changes? Specific temperature governs vapor pressure. Vapor pressure changes exponentially as you heat the system, which is our liquid vapor system. This is a graph of vapor pressure changes versus temperature. Now, what you'll see first, you need to notice that vapor pressure as a function of temperature is an exponential change. It changes very rapidly and increases very quickly as the temperature increases. Now, the three molecules represent systems. This one has a low polarity, a low polar system, a mid-polar system, and a high polar system. Now, what this means is the particles that interact, the more interaction that they have, the greater the harder it is to increase the vapor pressure. For example, if you look at a graphic let's say a couple of particles inside here like that. Well, these that are inside are certainly interacting very strongly in here. And so if you have another particles up here that are also strongly interacting, then that interactive polarity will govern how fast these particles will come out. So if you have a low polar system, molecule, you'll have a fast or a high vapor pressure. If you have a highly polar system, like water, you'll have a relatively low vapor pressure. Now that's in terms of polarity things. Another factor that affects vapor pressure is the size of the molecule. So for very large molecules, they actually have a higher interactive character, and so they too would have a low vapor pressure. Example is oil or some thick fluid. You can smell some of it, like some oil, you can smell the vapors of it, but it is very light. It's not very high vapor at all. But it's just the odor lets you know it does have a vapor pressure. When we talk about extremely low vapor pressures, we're talking about things like alcohol that has a low polarity in some cases. It'll exist as a liquid, but it'll evaporate very, very quickly. One of the things I meant to say about evaporation being a surface phenomenon, that's one of the reasons that when you try to wipe up a spill of water, you spread it out. You want to soak it up, of course, but also spread it out to expose more molecules to the surface, and it evaporates quickly. Alcohol, ethers, low molecular weight hydrocarbons, low molecular weight MW hydrocarbons, because they will evaporate very quickly because they don't have the particle-particle interaction that a highly polar system like water or ammonia would have, and for very large molecules they will have a higher vapor pressure also. Now, in the concept of vapor pressure, we now go to boiling point of a solution. By definition, the boiling point, this is a technical definition of boiling point. The boiling point of a liquid is the temperature at which the vapor pressure equals atmospheric pressure. So, boiling point vapor pressure of the liquid, of the substance. For example, water, of course, would increase its vapor pressure as temperature increased, and you'd see it go up like that. If it stayed in the liquid phase, it'd continue to increase the vapor pressure as it evaporated. But if this is atmospheric pressure, say it's 1 atmosphere right here, you'd find that the temperature is 100 degrees Celsius. Okay, because most people, we all know 100 degrees Celsius, 212 degrees Fahrenheit, or 373 Kelvin if you want to get technical about it. So this is the point at which water will certainly boil. Now, the reason it has a reasonably high vapor pressure, you have to force it into the solution. Force the evaporation from the surface until you get it to that boiling point. Now, one of the points here that you need to remember is the fact that a sample of liquid is producing bubbles as it boils. That ain't boiling. That is an impurity within the liquid. And some people may not know this, but if for pure water, if you started with a liquid right here and you had no impurities in the solution, over time, say time equals 0 and time greater than 0, what would happen is it would evaporate smoothly down to, from here down to here. You wouldn't see it. Just the level would just evaporate and disperse. The fact that you see bubbles maybe coming out of it, those are microparticles in there that are surface hot, and the liquid superheats around those impurities and causes the liquid to go into the gas phase very quickly. But in the true sense of boiling point, every molecule in here does have the energy to escape from the surface of this liquid, but in the pure sense of the concept, only evaporation is coming off of the surface. That's it. You don't see that, and it's almost impossible to demonstrate that idea. But in the context of what a real boiling point is, it is all the particles have enough energy to escape into the vapor phase, but they may be staying in the liquid phase but still evaporating from the surface. So all the particles can evaporate at the boiling point. Only the surface particles below the boiling point have the ability to go into the vapor phase. Now, from here, this is what we've seen before. If we were taking a block of ice, it would have to be heated first of all to its melting point right here, and then you'd have two phases in contact, solid liquid melting. If we're going left to right, and once all of the sample is melted, we will increase it to the boiling point, and this is another phase change. This would be the liquid gas transition until everything was in the vapor phase, and then we could increase the sample to whatever temperature. Only the pure condensed phases will demonstrate a temperature change. Those which are in two phases in contact do not. This is an energy change without a temperature change right here. This is new. Okay, that is called an adiabatic transition or an adiabatic change. I'll write it out. From the thermodynamic people, they made that big word up, and it means that you have energy changing in that system, going to kinetic energy, for example, but it is not undergoing a temperature change, as you can recognize. Say, here would be the 100-degree Celsius boiling point and so forth, and we recognize the Q energy, MC delta T equation, and Q equals M delta H vaporization. So if you need to, it's online. You go back and look at a lecture on this and the problem we worked, and some things on calorimetry. But there's some calorimetry worksheets on, and I will give you a couple of problems on calorimetry because it deals with phase change. I'll keep it straightforward, hopefully. And but anyway, that's as far as I wanted to go in this, simply because we've already covered it in reasonable detail in earlier topics. Unless anybody wants me to develop anything here, I'm going to move on to the phase diagram. That is definitely new. And what this is showing is a vapor pressure temperature combination for whatever state of existence water would be in. And if I ask you a simple question, what are the states of matter, you would most likely say solid, liquid, gas in that order. Well, that's the way this is organized, and it's just a little two-pronged fork coming up here, and a line coming back down to the origin of the axis, vapor pressure and temperature. The line represents the temperature vapor pressure for a phase transition. So if we're talking about a solid liquid phase transition, we are melting or freezing right here. If we're talking about a liquid to gas transition, boiling or condensation along the line in here. If we're talking about sublimation, we're talking about any temperature pressure combination along this line right there. At normal conditions, we call 1 atmosphere normal conditions, like the room conditions right now, ambient conditions. We have 1 atmosphere. And if we looked at this graph at when the temperature right here and atmosphere pressure is right here, it's kind of a low temperature, 0 degrees right here. Well, it's going to transition into a solid from a liquid. So in 0, that's freezing. When you get up here where you have the liquid gas transition, where the atmospheric line intersects this curve right here, you have the boiling temperature of the liquid. Now, one of the interesting things about this is you can lower the pressure and boil at different temperatures. So if I took my ruler and drew a line, say across here, like this, and if I drew a line across here and hit this point and this point right here, you would see an little increase in freezing point, and you would see a decrease in temperature needed to boil the sample. Here is a lower pressure. Of the system at a lower pressure. This is not coming out very well at all. Here, get us something else. Here, see it. At a lower pressure, this will give you a lower boiling point. That is the ability to transition from liquid into gas phase. And if I kept coming down in here, what would this mean if I got it across here into this position? Well, here is a low vapor pressure right here, and it would transition if it was a solid. That's what I'm trying to say. Say we had a block of ice right here. And if we lowered the pressure around that block of ice, it would sublime. It wouldn't melt. It would go right into the gas phase, because all of this region under here is gas phase. So there would be an immediate a solid to a gas transition at low pressure and low temperature. Well, this is the principle behind what is called freeze drying. You've certainly heard of Tang, the orange juice, freeze-dried, or freeze-dried coffee, or freeze-dried soup. All you do is add hot water and off you go. Well, what's happening Okay. Let's say you wanted to freeze dry, say, some soup. Well, you'd fix the soup at a nominal condition like this, at room conditions, and you would prepare it or heat it or whatever in the liquid phase. So you'd prep in the liquid phase. Then you would freeze it back here, or lower the temperature till you were freezing. That's number one. Number two is freeze it. Okay? And then number three, you would lower the pressure around the frozen food until it got down below this point right here. That would be number three, lower pressure. And the water around the food would go from a solid to a liquid and undergo sublime, and they would have, only thing that would be left would be the freeze-dried samples of the food, and then they would collect that, put it in bottles, sell it to you in the grocery store. So, and that is just one of the concepts that are explained by the phase diagram. Another one is a little. Anybody been to Yellowstone National Park? Anybody in here been to Yellowstone National Park? Nobody? Well, what's it famous for? Geysers, right? Yeah, most of you already know that. Okay. Well, this phase diagram will explain geysers also. There are a couple of points on here that you need to make note of. Let me bring this back up here. The triple point and the critical point. Triple point, you need to remember, you don't even remember the numbers, but you need to remember the term, is the temperature pressure at which all three phases exist simultaneously. So that's what that is. The other point is the critical point up here, 374 degrees Celsius and 218 atmospheres. So keep that in mind for short term. But here, if a liquid gets to the critical temperature, it cannot exist in the liquid phase any longer, and then it transitions into a gas phase explosively under those conditions. So 374 and 218. So come down here. I'm going to redraw this little diagram here. Let's say this is a surface of the Earth, and here we have a little channel through surface down to what we call a magma surface. In Yellowstone Park, the surface is kind of close to magma flow, and so this is a hot interior of the Earth. Very hot. Okay? Well, the water that gets down in here, it comes down into that crevice, is heated at the bottom. Okay? And undergoes what is called convective currents, like this. I think everybody kind of understand what convection is, you know, heat flow like that. Okay. Over time, many years, what happens is a barrier is built up because of precipitating salts inside this fissure. It's going down to the magma, and the water that's in there stops its convection at a lower point right here, and so it starts convecting. Well, it keeps heating, and it can't cool by going all the way to the surface, and so as it's heated, this convection is periodic, if you will. And so what was it, 317 degrees Celsius and a whole lot of atmospheres. See if I can find it again. 218 atmospheres. So this is heated, and then it explodes out into a geyser. And because of the convective current, we have that geyser erupting every periodic time. And you've heard of the old geyser, Old Faithful. Well, every 60 minutes, it's gotten a little bit different now, but on the average, 60 minutes, that geyser will explode out of that crevice into vapor. and it'll all spew out, empty the crevice, and then fall back down and fill up the hole and start the process over again. So that's how geysers function. They function by the action of heating the water to the critical point. Intermolecular forces. Okay, these are essentially physical forces. In the universe, we have three types of forces. We have physical forces, chemical forces, and nuclear. And these are attractive forces in terms of holding liquid into liquid form or ice into solid form. Chemicals is we've just finished talking about chemical bonding, but this is a particle-particle interaction between elements. So this is very strong compared to the physical. The physical is very weak. When we talk about numbers, it is 10 kilojoules per mole, say, 1 to 10 kilojoules per mole. Very, very, very weak. When we talk about chemicals, it's stronger than physical. Strong bonds, if you will. These will go from 300 up to 1,000 kilojoules per mole as a reference number. When you get to nuclear, these are super strong. Nuclear bonds holding the nucleus of an element atom together. And so these are some in 1 times 10 to the 6, just millions of kilojoules per mole of sample. And so what we're talking about in this topic is just to put these down to give you perspective. The physical are the forces that interact between solids, liquids, and gases. So physical forces simply define the solids, the liquids, and gas phases. Now, there are three physical type forces. There is a dipole interaction. There is hydrogen bonding. This is not the chemical bonding between hydrogen. Hydrogen bonding is an electrostatic issue, and I'll get to that in a minute. And then there are very weak, what we call London dispersed forces, or London forces. Okay. When we talk about dipole-dipole interactions, we're talking about the interaction of molecules that are polar in their inherent nature. Hydrogens will be polar in their nature, and all of these interactions, these physical forces, are electrostatic. That is a plus-minus interaction. A plus part of one molecule interacts with a negative part of. If we take methane, for example, it is a non-polar molecule, this tetrahedral shape, like that. So as a non-polar molecule, it exists in gas phase. It has almost no interaction with its neighbors at room temperature. Now, if I pull one of the hydrogens off and I put, say, a highly electronegative element like chlorine on there, chloride, then the electronegativity of that chloride will draw the electron density toward it and will make the end of the molecule negative, partially negative, and why this end is partially positive. So you can look at it as a group of plus-minus interactions like this, plus-minus, another one, plus-minus, maybe another minus plus, and it would go on like that, minus plus, and so that would be a dipole-dipole interaction. And this is methylene chloride. And at room temperature, it's a liquid. But all I did was replace the hydrogen with a highly electronegative group there, and it formed a dipole. And so the dipole-dipole interaction is such that it causes the particles to agglomerate, or as such, and form the liquid phase. A hydrogen bond, I'll draw one out for water real quick and kind of give you a graphic of it. Water is a bent angular molecule, a couple of non-bonded pairs on the oxygen, and will interact with the non-bonded pair on another water molecule, like this. And this plus minus interaction right here is the hydrogen bond. And hydrogen bonds are very strong compared to simple dipole-dipole interactions. Hydrogen bonds really push the interaction of molecules together and cause a rapid increase in boiling points, and we'll get to that in a minute. I'll show you a graphic. Hydrogen bonding is a two-part definition. Is the interaction electrostatic interaction, if you would, the electrostatic interaction of hydrogen with a very electronegative element on another molecule. And I'll give you those: nitrogen, oxygen, or halogen, chloride, bromide, iodine, like that. A very electronegative element on another molecule. And that's only half the definition, such that the hydrogen is covalently bonded itself to a very electronegative element. That's it. So two things have to be present to account for hydrogen bonding. One is that the hydrogen has to interact with a very electronegative element on another molecule, like this right here that I'm showing you, hydrogen interacting with that. But the hydrogen must also be covalently bonded. Let me see if I can get something to work. Must also be covalently bonded to a highly electronegative element in the interaction. So you have the electrostatic interaction here, and this one is the covalent. So without those two, you do not have a hydrogen bond. Hydrogen bonds are responsible for causing large increases in boiling points for certain substances. Okay, if you can see this, the machine will not zoom in. I think that's big enough. Size of the molecule as it increases, also increases boiling point, because you have heavier molecules, they won't evaporate, and you can't get to the vapor pressure very easily. However, if you have small molecules that have hydrogen bonding in them, you can have some rapid increases. Now here is, let's start right here. I was looking for, oh, here's water. Look at water, it's up here at 100 degrees, okay? It has hydrogen bonding like I was showing you earlier. Well, here it is over here. There's your hydrogen bonding graphic there, okay? And that pushes the interaction up to, so that it's hard to evaporate water, and it takes a lot of energy to make this molecule go into the vapor phase. So it has a high boiling point here. But look what sulfur, all you did was replace it with sulfur. And so you have an H2S right here, and hydrogen sulfide doesn't have the hydrogen bonding characteristics like water does. So it boils at a minus 60 degrees. But if the central elements changes to a larger molecule, then you see the boiling points start going back up. Here they are, same thing. Here's ammonia. It has hydrogen bonding in it right there. And if you change it to pH 3, it drops off radically until the arsenic trihydride right here, and then the molecules go way on up to antimony. Here, antimony trihydride have a high boiling point, but the size factor makes this boiling point goes up. But the ammonia and hydrogen fluoride have extremely high boiling points because of hydrogen bonding right here. And then here's hydrochloride, hydrochloric acid, it drops, and then hydrogen bromide bigger, and hydrogen iodide, and so forth. Here's the CH4 way down here. It has no interaction at all, no dipole. And so it's exclusively size oriented in boiling point. So this is a minus 60, then it goes up to looks like about 110, minus 110, and so forth. But two things are important in understanding boiling point: size of the central element and hydrogen bonding. And hydrogen bonding will override anything else. Now I'll show you a question for you. Which of the following has the highest boiling point? Okay, now you may not know a thing about any one of the molecules, but you only need to know one simple thing. Which of these has hydrogen bonding in it? And that's the choice here. The hydrogen bonding in here is a result of the interaction of hydrogen with another ethanol. This ethanol, hydrogen will interact, and then this is covalently bonded back here. But this is, these two are dipole-dipole interactions because of their geometries and the fact that they have outlets. This is a totally non-polar molecule at the very top up here, and it has no hydrogen bonding or interactions whatsoever. So when you get a test question like this, and they give you a list of, first thing you look for is that OH in there. If you find that OH in there, that's going to outride everything, okay? If you have a, also, if you have a, say, a list, and I showed you this just a second ago, H2O, H2S, H2, whatever under sulfur is, Se, and H2 Te. Of course, that will have the highest boiling point, but sometimes the questions will come to you like this: which of those has the second highest boiling point? Okay, well, this one has the highest boiling point because it's hydrogen bonding, but size then takes over. I showed you that in the graph. Size then takes over to push up boiling points here. So don't get snookered by that idea. See here, size takes over, and the Te is larger than the selenium and the sulfide. Okay, so kind of check mark that in the back of your mind as you approach exam day. But I do throw a couple of those in there for keep you honest. But anyway, this would certainly be the highest, but this would be the second highest boiling point. Everybody good on that? Kind of, sort of? London forces are van der Waals forces. These are referred to as dispersion forces and have to do with systems that have very, very low polarities, but we can push them into liquid states like nitrogen. You've heard of liquid nitrogen, liquid oxygens, or liquid methanes, and some of those. Well, how do you get them into those liquid states? Have a good one. Okay, if I have, say, neon is an inert element, and it comes close to another neon. Well, normally at room temperature and pressures, it's this exact gas phase, but at very high pressures and low temperatures, okay, like that, what happens is the nucleus of one molecule distorts the electron cloud of another, and what you have is a system that will do this. It'll be build up of negative charge on one side and have a very few negative charges on this side. This would have a high negative charge like this, very few on this side. Well, since this kind of repels these electrons over here, this is all theoretical. Nobody's ever proven this, but this is what's in the book, so you enjoy. Anyway, it produces a positive N and a negative N, positive N and a negative N. And so at very high pressure and very low temperatures, systems which are non-polar come together by dispersion effect. That's what this is, dispersion effect, or dispersion forces. And they exist, but we have to maintain the high pressure and extremely low temperatures for a non-polar system. And it is an induced dipole is what it's called also. Induced means it's forced. Okay. So that almost gets us through this chapter. We just want one more topic to talk about. Kind of a weird name, but okay, we take what we get. Clausius, C-L-A-U-S-I-S, A-U-S-I-S, Clapeyron equation. This is a relationship, an equation that defines vapor pressure of a liquid in terms of its temperature. So this is vapor pressure proportional to a function of temperature equation. Not a real difficult equation, but you're going to have to work problems on it. And the equation is derived out of vapor pressure relationships and temperature, but it boils down to this. It's a natural log of vapor pressure 1 over, vapor pressure 2 over vapor pressure 1 to equal delta H of vaporization over the universal gas constant times 1 over the first temperature that goes with the vapor pressure 1 minus 1 over temperature 2, which goes with vapor pressure 2. Now I like to express this equation in the following. It's easier to, in my opinion, to work with by taking a common denominator, and it turns into T2 minus T1 over T1 times T2. It's just multiplying the two temperatures together, getting the common denominator, and you wind up with that expression like that. So, in my opinion, it's a little bit easier. Okay. So this is the kind of problem you'll have to deal with on the test, and be very straightforward if you learn the equation. Okay. Calculate the vapor pressure of water at 85 degrees. Given the normal vapor pressure for boiling point is 760 millimeters. Okay. Now you'll need to have the heat of vaporization under normal conditions 40.7 kilojoules per mole, and there is your R value. And the difference here is this is listed in joules, and you'll find the R value listed in joules per mole Kelvin in most textbooks. But when you apply it to this equation, you need to convert it to kilojoules which of course is 0.008314 kilojoules per mole Kelvin, like that, and substitute that number into the equation. So what we're looking for, of course, is this second vapor pressure given V1 and T1 and T2. Now, the temperatures have to be in Kelvin, so you have to make your conversions to. So we're just trying to find out who's who in this. So Ln Vp2 is our objective, and vapor pressure 1 is 100, so that'd be 373 Kelvin right there. Okay, everybody kind of follow that? 3 Kelvin. Okay. Now that equals to the heat of vaporization, which is simply the 0.008314. Come on. I'm sorry. 40.7 kilojoules per mole. Duh. Anyway, now put in the 0.008314 kilojoules per mole Kelvin. So that kind of gets us to here, and so now the T2 is 85, so 273 and 85, 5, 6, 7, 8, 2, 7, 14, 15, 2, 358, 15, 358, I guess. Okay, so T2 is 358 minus 373 divided by product of those two, 358 and 373. So it's just a case of keeping up with the equation. Okay, now you got to work with the equation. Practice this a little bit. I'm not going to give it to you on the exam. You got 2 over 1, and the original was 1, 2 in the temperature changes. Yes, sir. Never mind. Well, anyway, simplify this part of the equation first, and then work it down into the natural log. Let's see if we can. So this comes out, and if y'all back me up on that, would you run it through your calculator sometime? Let me know if it's okay. But anyway, and when you get this far, what this is ln of Vp2 minus ln of 760 is equal to a minus 0.55. So all we need is ln of 760. Here's that 6.63. So it's ln of Vp2 minus 6.63 to equal a minus 0.55. And of course that will go over, I'm going to have to move it up a little bit, guys. Okay, so ln of Vp2 is equal to 6.63 minus 0.55. So 6.08, 6.08. Well, anytime you have a logarithm and you want to untangle that, that's an e function. So this just converts to Vp equals e to the 6.08. It's an exponent of the natural log, and all I have to do now is hit my e function, and I get 438 millimeters at 85 degrees Celsius. So you will have to deal with this kind of problem. I'll ask you to calculate a vapor pressure, but also keep in mind I can give you T1 and T2, and you'll have to calculate delta HV. Here all the temperature pressures are given, but calculate the heat of vaporization. So there's 2 kinds of problems that you'd have. I could actually go to 3 kinds, but I'm not going to go beyond that. I could ask you, well, what temperature would the vapor pressure be? Give you a second vapor pressure or something of that nature. Anyway, it's just an algebra problem. Once you get the equation down, so when you get your exam, jot it down as quick as you can, so you can go back to it when the time comes. Okay, so here are a couple of terms, properties of liquids. Liquids are defined by two terms when you're studying liquid characteristics, and that's surface tension and viscosity. Surface tension is more of a resistance to spreading, and it's got some terminology in terms of how much force is needed to spread a liquid. And I think the simplest thing that you could do in surface tension is resistance to spreading. Okay. Things like soap have high surface tensions and particle-particle interactions, and they're hard to spread. And when they do, they hold together, and that's how bubbles form. They have a high surface tension. Viscosity is the second term in here, and that is resistance to flow. And if you have a bottle of water and you dropped a marble in it, it'd go down pretty fast. But if you had some syrup, a can of syrup or water, or a can of oil, and dropped a marble in that, it would go down a lot slower. Well, the oil and the syrup have a higher resistance to flow, or higher viscosities. And so liquids are characterized mostly between the surface tension and viscosity terms. Questions on the exam will be definition type oriented. I'll give you something like, which of the following would have the highest viscosity? And I'll give you some alcohol, water, syrup, or something of that nature. And you just pick the thickest fluid. And so that would be the highest viscosity. And properties of solids are terms that are used to describe solids. Now, both of these topics can get into an extensive cross-section of technology, and there's no question about it. But just going through the basics here. If you go into formulation, chemistry, and those kind of things, you'll have to really involve yourself in the chemistry and physics of liquids and so forth. Okay, well, when we talk about solids, there are four kinds of classes. There's a molecular solid, there's metallic, there's ionic, and covalent network. If you think about it, these are pretty easy characterizations. Molecular solids are pretty much organic molecules, things that you can isolate individually. CO2, H2O, ammonia. All of those are molecular type materials, and you can freeze them down. Ice is a molecular solid. CO2 in its solid form, or ammonia can be pushed down, but rocks, pebbles, all of that is molecular solids. Metallic, well, that's any kind of metal in wire form. What copper, silver, coins, and so forth, metal. Ionic solids are salts, crystalline salts, and covalents are like graphite, diamond, things of that nature are mostly covalent. Diamonds have a tetrahedral geometry. I may have a picture of that versus graphite. Yeah, I do. here is a three-dimensional of the diamond. As you look at this one right here, and here is the carbon in the graphite. And so it's a planar type structure called graphene. Each one of those planes, graphene, and it has a lot of electrostatic nature to it. And here is your diamond, of course, in a three-dimensional structure. Very hard, very high tensile strength, and so forth.